So let's continue. We have been given a transfer function. So it's still a third order transfer function. So 2s cube plus 10s square plus 21s plus 23 over s cube plus 5s square plus 7s plus 10. So again, let's observe few things. This is the coefficient 1, so it's standard form. And we can see because of this, it's just a proper transfer function. So let's write down what the coefficients are. So we have B0 is 23, B1 is 21, B2 and B3. Then we have A0, A1 and A2. Alright, so the CCF form is a third order system. 0, 1, 0, 0, 0, 1, minus 10, minus 7, minus 5. BCCF is 0 everywhere except the last entry, that's 1. Now let's come down to the C vector. So B3 is not 0 here. So let's see what the first entry is going to be like. So it's 23 minus 2 into 10 and 21 minus 2 into 7 and 10 minus 2 into 5. Okay. So this is going to be a row vector. So this is 3 and then we have 0 here. This is 21 minus 14, so 7. And then DCCF is always 0. Okay, so alright. We can also see what the OCF form is going to be like. So you can just calculate these. Alright. Okay. So if it was a higher order system, for example, for a fourth order system, so this ACCF is going to be, for example, 0, 1, 0, 0, all zeros. The second last row is going to be 0, 0 and 1 at the end. And you already know what these coefficients are going to be. Then you also know that BCCF is going to be all zeros except 1 at the end. So just remember that CCF is going to be B0 minus A0. And this is, I'm going to write this down as Bn. So if it's an nth order system, for example B4, this is going to be A0. Then for n equals 4, you would have B1 minus B4 times A1. Then you would have B2 minus B4 times A2. And then you will also have this B3 term. So this is how you can extend for the nth order system in the case where the transfer function is just proper and DCCF is always 0. Okay. Now let's move on to the next question. So we have a transfer function again. It is s plus 3 over s plus 2 squared s plus 5. So we have to write down the controllable canonical. Alright. So we already know what B is going to look like. So BCCF is just going to be 0, 0, 1, and DCCF is going to be 0. So let's just write down the transfer function in the standard form. So we have s plus 3 over s squared plus 4s plus 4 and s plus 5. This is going to be s cube plus 5s squared plus 4s squared plus 20s plus 4. This is going to be s cube plus 9s squared plus 20s plus 4. Alright. So now we can comment on this. So this is in the standard form, and there are no s cube or even s square terms. So of course this is strictly proper. Okay. So now we can write down what the matrix ACCF is going to look like. It's a third order system. The order of the denominator polynomial is 3. So 0, 1, 0, 0, 0, 1, then minus 4, minus 20, and minus 9. And now we have CCF. So 3, 1, and 0. So just see that this is 0 square. So don't forget this one. Just remember this is going to be a 1 by 3 vector. Similarly, you can of course write down the OCF form. Now let's look at another question. So this is fifth one, question 6. Alright. So we have the transfer function ys over rs as 50 times 1 plus s over 5, 1s times 1 plus s by 2 plus s over 50. Okay. So again the question is that write down the CCF. So let's convert this to the standard form of the transfer function. To do that, let's see this 50 over 5 s plus 5 upon s plus 2 by 2 s plus 50 by. So we have 10 s plus 5 s plus 2 s plus 50 minus 100. Okay, so we can simplify this further. We have g of s equals 1000 times s plus 5. I'll just write this down as 1000s plus 5000 well, s square plus 50s plus 2s plus 100. Alright, so this is a second order system. Alright, then we have one here, so this is the standard form, and this is strictly proper. Alright, so this is going to be just a 2 by 2 matrix, ACCF. This is going to be 0, 1, and then minus 100, minus 52. Oh, okay, sorry. So this is actually a third order system. Miss the S over here. So let's write this down. S times. So this is S cube plus 52s squared plus 100s. And we also have 0 here. To get to the standard form, this is also standard. And of course, this is strictly proper. So now ACCF is going to be a third 3 by 3 matrix. So 0, 1, 0, 0, 0, 1. We get 0, minus 100, minus 50. So this is important. You don't mess out the coefficient which is missing in the denominator polynomial. Alright, then BCCF is easy. It's just 0, 0, 1. Then it's okay. So DCCF is just 0. And now let's see what this is. So we have a strictly proper transfer function. You will have 5,000, 1,000 and 0. This is 0 square. So just note this down that this has to be a 1 by 3 vector. Alright. So we have seen various examples of transfer functions and how to convert them to state variables. Now let's see that if we have differential equations which have derivatives of the input on the right hand side, then how do we obtain the CCF and OCF forms for that? So we'll see that through some questions. So let's write them down. This is going to be question 7. So construct state space models for the following differential equations. So these can be CCF or OCF. Alright, so there's A triple dot plus 3 double dot plus 2y dot equals u dot plus u. Then we have the second part to this, y triple dot plus 6y double dot plus 11y dot plus 6y equals u. And the last part is y triple dot plus 6y double dot plus 11y dot plus 6y. So it has all the derivatives of the input on the right hand side. By this I mean the third order derivative plus 8u double dot plus 17u dot plus u. Okay, so we have differential equations. And we already know how to convert transfer functions to state variable forms, to CCF, OCF, and so on. So now you just need to do this part. So this is going to be through Laplace transform. So from here to here, you obtain the GS by Laplace transform. Alright, so let's look at the simplest example first with no derivative of the input. So let's consider D. Alright, so let's see the Laplace transform on both sides. So for transfer functions here, zero initial conditions. This is simply going to be s cube plus 6s squared of 5s plus 11sys plus 6ys equals 2 of s. So this is going to be 1 over s cube plus 6s squared plus 11s plus 6. Okay, so we have the transfer function now. Let's just check. This is in the standard form. And we are that this is strictly proper. Alright, so we know now how to obtain the CCF forms. So a third order system. So 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6. This is straightforward, 0, 0, and 1. Now let's talk about CCF. So just remember the general formula. So we have B0, then we have say 0s and 0s squared. So this is going to be the C vector, and of course the CCF is just 0. You can just bring the OCF forms. Now let's look at, so this is done. We look at the system where we have the first order derivative of u now. So let's see. Let's just rewrite the differential equation. Y triple dot okay. So now let's take the Laplace transform on both sides. So we have s cube plus 3s squared plus 2s. Here it's going to be s plus 1, and the transfer function is going to be s plus 1 over s cube plus 3s squared plus 2s. Just observe that this is going to be 0. It's still in standard form, and we have that this is strictly proper. Okay. So let's see, we have ACCF, third order system. Then we just have 0, -1, -3. And then we have DCCF. This is simply 0, 0, 1. We know that DCCF is 0. Now let's just look at what C is going to be. So let's just write this down. Strictly proper. So this is going to be 1, 1, 1 and 0. Alright, so we have to take care of this term in the C vector. Okay, now let's look at the most complex case. We have part C, where there are also third order derivatives of the input u, and you can just see that this is going to be a proper transfer function. Let's just rewrite this. Okay, C. So again, let's take the Laplace transform both sides. We have fs s cube plus 6s squared plus 11s plus 6. Then we have u of s is going to be s cube plus 8s squared plus 17s plus 1. Alright, now we can just form the transfer function. This is g of s over s cube plus 6s squared plus 11s plus 6. Alright, let's check. This is the standard form. Yes. This is proper transfer function. Okay. So let's form the matrices. It's going to be -6, -11, and -6. This is 0, 0, 1. You already know what this is. And now let's see what C is going to be. Okay. So it's going to be 1 minus 1 into 6. Then 17 minus just 11 and 8 minus 7. So we have -5, 6 and 2. So you can see that a proper transfer function affects what the C vector is going to be. Alright. So now let's look at another question. So this is the transfer function s plus 4 to s plus 1, s plus 3. Okay, so let's see. Let's convert the transfer function to the standard form. So we have s plus 4. Okay. So let's see, this is divided by 2. We have s squared plus 3s plus s plus 3. This is going to be 0.5s plus 2 upon s squared plus 4s plus 3. So this is going to be s cubed plus 4s squared plus 3s. Okay, so now let's check. This should be 0. And then you have the standard form. So what we did to get the standard form was to take this and divide the numerator by this quantity, so that the highest power of s in the denominator has coefficient 1. And from this we can observe that this is also strictly proper. Okay, so now it's easy to form the matrices. We'll first calculate what the CCF matrices are going to look like. So ACCF is going to be the third order system. Degree of the denominator polynomial is the order of the system. C010, 001, 0 minus 0 minus 1. Then we would have process 001. We already know what DCCF is going to be 0, and this is going to be, so it's strictly proper. Note that this is going to be 0 squared to 2.510. Okay, so we can obtain the OCF form now. It's going to be 010, 001, 0 minus Cn minus 4. Then we have VOCF as this vector. Then we have COCF as 001. and DACF crystals. Okay, so I hope this question was clear to you. Now, so these are all the questions for today's session. So let's just review what we have done. Okay. So we started with the introduction to the control system theory, in which we said that we always need a model of the system that we're talking about, and our objective. I'm just going to write this down. This is the objective, to design control laws such that our system so control laws such that the system behaves in the desired manner, or the system has desired performance. Alright. So after this, we looked at what kind of models we'll consider. So we'll either consider models which just have input-output relationship. For example, transfer function. We have this as G of S. And the other one is based on the mathematical model of the system, particularly in the case in which we consider internal parameter of the system. For example, for an electrical circuit, the model which depends on the value of R elements. Okay, so one such example is this state space model, and this is what we have seen in this example. So this was a simple electrical circuit, and we said that to obtain the status of the circuit, what we need are voltages and currents of all the elements. And we argued that instead of knowing all these voltages and currents, we only need this set, E1 and E2. And we said that this minimal set is the set of states of the system. Then we find out what the evolution of these states are going to be. And at each time, if we know E1 and E2, we can just reconstruct what these other quantities are going to be by some simple algebraic conditions. So we have Y here, I1 and I2 here, and we also have E3 here. Okay, so to get the evolution of the states, we form these matrices A, B, C, and D, and we say that the state space equation, the standard form of x dot equals ax plus bu, and the output y is cx plus du. So to get the state space model, we need to know the matrices A, B, C, and D. Alright. So this was just some remark on the different models that were considered in the lecture. So we have the state space model, in which we can have linear time invariant systems, linear time varying systems, and then we can have various forms in which we write the ABCD matrices. This could be CCF, OCF, and so on. And we can also have some higher order differential equations. So this is higher order differential equation, and this in particular n first order differential equation. And then of course we have the transfer function. So this can be, the transfer function can be proper or strictly proper, as we have seen. Okay. So beginning with the state space model written in the CCF form, there are various names for it. We started with the most simplest case of the differential equation, in which there were no derivatives of the input. So in this case, we called what the ABCD matrices were, and then we did a question. So the main point is that the coefficients of the last of the A matrix start from the right hand side of the differential equation y, and it's the negative of the coefficient. Then B is simply all zeros except 1. So this means that the state xn dot has some summation alpha i's x i's, I ranging from 1 to n, plus u. So the dynamics of the last state is affected by the input u. And then for the CCF case, we take output as the first state. And there is no coupling between the input and output. So then we look at some basic examples. So the standard form was one of the most important parts of this. So given any differential equation or transfer function that needs to be converted to the state space form, we first need to write it in the standard form. So standard form is that the coefficient of the highest order derivative should be 1. So this was explained in this question, and we formed the CCF for the above equation. Then we found out what the relationship between observable canonical and controllable canonical form are. So this was just basically transpose of the A matrix, but the B and C matrices were related by these two equations. Alright. So we know how to form the controllable canonical and observable canonical forms for a very simple differential equation, nth order differential equation. And now we'll see the conversion between transfer function and canonical state variable forms. So we discussed two reasons for this. So one of them was this, that in MATLAB you can just, for example, simply use OT45 to solve n first order equations, n first order differential equations. And then the first one was that there are specific techniques which are suited for the state space analysis. And then we found out that given a transfer function, we can construct a state space model. The state space model is not unique. And then we saw how to obtain the CCF and the OCF forms. So this was a general expression for a third order transfer function, in which the coefficient for the highest order term in the denominator was 1. Then these were the ABCD matrices. And for a strictly proper transfer function, the C vector can be simplified to this form, B0, B1 and B2. Then we, I think, looked at some more questions. So for strictly proper transfer function and in standard form, then for proper transfer function in standard form, then we first wrote down this expression in the standard form. The standard form, I mean polynomials in S, in both the numerator and the denominator. Okay, so after this we looked at how to convert differential equations to the CCF and OCF forms. So we already know how to convert transfer function to CCF form, and by obtaining Laplace transform of the differential equations, we can follow the same procedure. So we did 3 questions regarding this. This was the simplest case. which we had already seen. Then we ordered a first derivative of the input. So this was still strictly proper. This is still strictly proper, but this was a proper transfer function. So okay. So the last question, we saw how to convert the transfer function to a strictly proper one. So we saw that the coefficient of the highest degree, the denominator was not 1. So this is how we converted it to standard form. And then the rest of the procedure was. So to get OCF, we first obtain CCF and then obtain the OCF version. Alright. So this is it for today. Thank you.